Hi, I'm Dr. Frank Summers of the Space Telescope Science Institute. Welcome to Hubble's Universe Unfiltered. Or perhaps I should be saying welcome back. We've been on hiatus for several months. But there's a really good reason why we were on hiatus. We were working on the IMAX film Hubble 3D. Myself and gentlemen behind the camera were heavily involved in creating the sequences of Hubble imagery in 3D for that film. The film came out in March of 2010, and our work on that film will be the subject of some upcoming episodes of Hubble's Universe Unfiltered. For today's episode, I'd like to talk about another special event that we had this spring, Hubble's 20th anniversary. This image shows you April 24th, 1990, the launch of the Space Shuttle Discovery carrying Hubble aloft into space. And this shuttle mission put Hubble into orbit into its platform from which it observes the universe. It has been up for 20 years now, taking an incredible number of observations. So how does one celebrate 20 years of such an amazing telescope? Well, I was asked to come up with 20 images to sort of show the breadth and depth of what Hubble has done over its observing history. And the first idea was to come up with all the most scientifically interesting images. Well, the most scientifically significant images oftentimes aren't the most beautiful images, and it often takes an entire episode of this video podcast in order to explain why these images are so significant. The other idea would be then to go for the most beautiful images. Well, then you tend to look only at the later part of Hubble's life when we had the newer instruments on Hubble, and you sort of ignore the early parts of Hubble's observations. So what we ended up coming up with is sort of a combination of those images that cover the full 20 years of Hubble, that cover all of the different subjects that Hubble has looked at, from planets to stars to nebulae to galaxies, and one that sort of covers the breadth of how much we've done in terms of scientific significance as well as beauty. Now, there's something that I have to get out of the way right away, is that after Hubble was put into orbit, there was the flaw in the mirror. And it's sort of a mythos that Hubble was unusable for the first few years until that flaw was corrected. That's not true. And you can see in this image of a double star that Hubble did provide advantages during its first few years. On this side, you see a double star as observed from the ground. And you can see here that it's really just one blob, and the two stars are merged together. That's because from the ground, we have the atmosphere in between us, which limits our resolution to about 1 arc second. On the other side, we have Hubble's observation of the exact same double star, and you can see that although the stars aren't the perfect little pinpoints we want them to be, you can resolve the two stars. Even with the flaw in the mirror, Hubble had finer resolution than any telescope from the ground. So Hubble was able to do good science for the first 3 years before it was repaired. And as one example, from 1992 is this image of the galaxy Messier 87. Now, Messier 87 is a giant elliptical galaxy. It contains, hundreds of billions of stars, maybe even 1 trillion stars. And at its core is a very bright source that we believe to be a supermassive black hole. This is a black hole with many, perhaps even 1 billion solar masses, 1 billion times the mass of our sun, in a black hole. And with all the material swirling around it and all the energy of that supermassive black hole, it is spewing out this incredibly jet of radiation from that supermassive black hole. And Hubble was able to take a highly resolved view of that jet in the galaxy Messier 87. Well, in 1993, we did have servicing mission 1, and the astronauts went up. And this picture is of them either taking out Wide Field Camera 1 or putting in Wide Field Planetary Camera 2. It's kind of hard to tell because they look pretty much exactly alike. Wide Field Planetary Camera 2 had the correction for the flaw in the mirror already built into it. The astronauts also put in an instrument called CoStar, which had basically eyeglasses for the other instruments, and that gave Hubble back the resolution it was supposed to have. So this next image is, I sometimes jokingly call, the most important Hubble image ever, because this shows you that the repair was successful. On this side, we see an image from Wide Field Planetary Camera 1 of the core of the galaxy Messier 100. And you can see the structure in there, but you can't see all the fine details. On this side, we see the image from Wide Field Planetary Camera 2, which had the correction, and you can see, voila, all of the incredible details. This is the fine detail for which the Hubble images are really known, and sort of crispness that characterizes all the Hubble images you've seen over the decades. So this image really said to the astronomical community, yes, Hubble is achieving its design specifications, and from there on, it was able to do the science that we had originally hoped it would do. So here come a slew of images, but actually there was a wonderful case of serendipity in 1994, because in 1993, comet Shoemaker-Levy 9 went into orbit around Jupiter, and it broke up into 20 or 30 pieces. And it was calculated to hit Jupiter in July of 1994. It was a very nice comet because it waited until Hubble had been repaired so that Hubble could take gorgeous and highly detailed images of the impact sites. You see those impact sites here in the lower part of Jupiter, and in visible light, they show up as basically big brown clouds in its atmosphere. In ultraviolet light, on this side, you can see that the holes in Jupiter's atmosphere are actually much larger. And it's important that ultraviolet light is not viewable from the ground. I know you think you get lots of ultraviolet light when you get suntan. Most of the ultraviolet light is absorbed by Earth's atmosphere. So to do astronomical observations of ultraviolet light, you must get up into space, and Hubble's platform in space allowed it to view these impact sites in ultraviolet and see the real detail. By the way, this is not an impact site. This is just the shadow of one of Jupiter's moons going across the surface of Jupiter. Well, 1995 was a watershed image that came out called the Pillars in the Eagle Nebula. Some people call this the Pillars of Creation. And what's going on here is that there is dense gas inside these pillars that is being illuminated by some bright stars that are up here. Matter of fact, the high energy radiation from those bright stars and winds from those stars are sweeping across this region, blowing away all the low density gas, leaving the high density gas in these pillars. And this gas is such high density that stars are forming. And you can see at the top of this tallest pillar that there are little fingers here, and that is where individual stars are forming. This image really, captured people's imagination and is perhaps the most famous of all of the Hubble images. In 1996, we captured this amazing image. This is of the dying star Eta Carinae. Now, the star is deeply embedded in here, and what you see more is the lobes of gas that have been blown out from the star during its death throes. This star is believed to be 100 to 150 times the mass of our Sun, and sometime in the next 1,000,000 to 10 million years, we expect this star will explode. It will go as a supernova and just basically blow its guts across space. So this is a star in its preliminary death throes. Well, 1997 was the year of our second servicing mission to Hubble, and in terms of imaging, we put in two brand new instruments, the Near-Infrared Camera Multi-Object Spectrograph, which we usually just call NICMOS, that was an infrared camera, and the Space Telescope Imaging Spectrograph, which we usually call STIS, which had both ultraviolet and visible light coverage, but was especially sensitive in the ultraviolet. That ultraviolet capability showed up the next year in this image of Saturn. This is an ultraviolet image of Saturn, and in particular of the aurora on Saturn. Now you got to recognize that Saturn is about 10 times farther away from the Sun than Earth is. And so the solar wind is expected to be about 1/100th the density it is at Earth. So we did not expect that the solar wind would be strong enough to produce a lot of aurora on Saturn. However, when we look at these images, the power in Saturn's aurora, as well as the changes in Saturn's aurora, surprised us as astronomers. And using the ultraviolet capabilities of Hubble, we're able to study that. In 1999, we got this wonderful image of a globular cluster. Now, a globular cluster is a dense collection of stars. This one has about 50,000 stars. Its name is Messier 80. And all of these stars are orbiting around one another. It's important to have high resolution when you are studying globular clusters because you see at the center of this image, it's sort of blown out. It's all white. You can't make out individual stars. Well, that's true in all globular clusters, that they're all very dense in the core. And Hubble's high resolution allows us to look deeper into the core of globular clusters than any other telescopes. Its high resolution allows more detailed studies of globular clusters closer into the center. That's what Hubble provides for globular clusters. And also in 1999, we got an image of the Ring Nebula. Now, this is sort of the characteristic, one of the template ideas of a planetary nebula. Now, planetary nebula is actually a misnomer. It has nothing to do with planets. What it really is a dying star. A star about the mass of the sun, or actually a little bit more massive than the sun, dies by blowing off its outer layers into space, forming a gorgeous nebula that we call a planetary nebula. And you've got the stellar remnant in the core and the beautiful gas around it. And if I had to choose one set of images of one type of planetary object, it would be planetary nebula, because Hubble has 20 or 30 gorgeous images of planetary nebula, and this is prototypical of it. Well, in December 1999, we had servicing mission 3A. What had happened was that the gyroscopes on Hubble had failed. Hubble could no longer point, and we had to send up a servicing mission to restore Hubble to its scientific capabilities. However, servicing mission 3A did not add any new imaging capabilities. It just got Hubble back into doing scientific observations. So in 2001, we released this image, which you could definitely refer to as a space oddity. This is an image of a gravitational lens. What's going on here is this is the galaxy cluster Abell 2218, and there are hundreds to thousands of galaxies here, and the combined mass of all these galaxies warps space. Via Einstein's theory of general relativity, mass warps space, and this cluster has enough mass to warp the space such that the galaxies that are located beyond it, as their light passes through this warp space, their images become stretched out, and these become these gravitationally lensed arcs that you see all across this image. Hubble is a very important tool for studying gravitational lenses because its high resolution can see these small, thin, and sometimes very faint gravitationally lensed arcs. Also in 2001, we had another serendipitous event here in the solar system. This is how Mars looked in June of 2001, and it's a fine picture of Mars, and Hubble is able to sort of monitor Mars and monitor the other planets and watch what happens on them. And in September of 2001, a dust storm that had started down in the Hellas Basin became global. This is a global dust storm on Mars, which we had seen at other times in Mars, but Hubble, from its perch above the atmosphere, is able to get clear images of Mars and able to monitor it over the years and catch these events as they happen. In 2002, we had servicing mission 3B. As I said, servicing mission 3A was just the technical part of the servicing mission. Servicing mission 3B, we put in a new camera called the Advanced Camera for Surveys. Now, Wide Field Planetary Camera 2, that had been the workhorse camera on Hubble, had a resolution of 1/10 of an arcsecond, and ACS has a resolution of 1/20th of an arcsecond. So we had twice the resolution with this new camera, and it covered much larger, it had 16 megapixels in the camera, so we had a great increase in the imaging capabilities of Hubble after servicing mission 3B. And one of the first images we released was this image of the interacting galaxies called the mice. What you're seeing here are two galaxies that have come into each other's gravitational influence and have started to interact and created these big long tidal tails that stretch off this side and stretch off this side, and the two cores of the galaxies here in the center. These two galaxies will eventually merge together, and Hubble will be able to see all the details deep down into the cores of these two merging galaxies. In 2003, we got an image of a more regular galaxy. This is a lenticular galaxy called the Sombrero Galaxy. And it has sort of a disk here that is characteristic of spiral galaxies, but it also has this great big bulge of stars that's characteristic of elliptical galaxies. Those are the two characteristics of a lenticular galaxy, that it has the disk like a spiral and the bulge like an elliptical. And what this image marks for me is really the movement towards getting large mosaics of Hubble images. Because although we're showing you about 1 megapixel here, in total, there's about 70 million pixels in this image. This is several pointings of Hubble put together to create a large mosaic of this image, and these would become much more prevalent as the years go on. Now, in 2004, we got one of the most scientifically significant images ever taken with the Hubble Space Telescope. This is the Hubble Ultra Deep Field, and in it you can see thousands upon thousands of galaxies. There are a few stars. You can see one here and one here. They have the spikes, the diffraction spikes on them. But most everything you see in this image is a galaxy. And, well, we've got the big galaxies that look sort of like our normal galaxies. But if we zoom into this image, we can go in until we go past all of those big galaxies until we see these fine, small galaxies. And really what we want to end up looking at is a galaxy like this right here. It's really just a small red dot. This galaxy is about 10 or 11 or maybe even 12 billion light years away. We're seeing galaxies all the way across the universe in this image. And that's what makes the whole image so important. That as we look at this image, we're seeing galaxies throughout the universe out to 10 to 12 billion light years away from us. And because they are 12 billion light years away, the light from those galaxies takes about 12 billion years to reach us. So we're seeing these galaxies not as they are today, but as they were 12 billion years ago. We are seeing galaxies across the space of the universe, but we're also seeing galaxies across the time of the universe. This one image gives us a history of galaxies throughout the universe. In 2005, we got what I gotta say is my favorite image of a galaxy that we've ever taken. This is the Whirlpool Galaxy, and it's a classic grand design spiral galaxy. You see the wonderful spiral arms. Now, again, this is a mosaic image. It contains about 100 million pixels, much more resolution than you can see on this monitor. And every single one of these pink regions that dot the entire spiral structure of the galaxy is a star-forming region. And you have to recognize that all of these star-forming regions have thousands to tens of thousands of stars that have formed in them. And when you start to go in detail and see all of the star-forming regions across the spiral structure, you can really start to comprehend that galaxies really are made up of hundreds of billions of stars. I really love this image because it really shows you the structure of a spiral galaxy, and it shows you the scale of galaxies out there in the universe. Of course, we kept coming out with really other fantastic images, and another one of my favorites is the Crab Nebula. Now, previously we showed you Eta Carinae, which was a star that's about to go explode. Well, this is a star that has exploded. This was a star that was observed about 1,000 years ago to explode, and this is the nebula created from the explosion when the star just basically blows its guts across space. And this is 1,000 years later as the remnants of the star have spread out across space. And I gotta say, these remnants are moving at millions of miles an hour to create what we call the Crab Nebula. And I gotta say, the hits keep on coming at this time, because the next image I have to show you is another fantastic image, the image of the Orion Nebula. This is our really large mosaic. I think at full resolution, we approach 1 billion pixels in this image. And this is perhaps our most detailed and spectacular image of a star-forming region, simply because the Orion Nebula is the nearest of the large star-forming regions. And so deep down in here, we can see the stars that have just formed. The stars in here are about 2 million years old. We can also see the disks of material around these newborn stars where planets will be forming. we have an incredible view of how stars and planets form by studying this image of the Orion Nebula. Well, in 2007, we got another gorgeous image of a star-forming region, but this one's at a slightly different stage than the Orion Nebula. In the Orion Nebula, they were still surrounded by its gas. In NGC 602, we have the star cluster here, but it's already eaten away most of the nebula. They form the pillars that you saw before in the Eagle Nebula. You can see the pillars up here and down here that are created by the energy and the winds from these bright stars in this cluster. Now, in 2008, we had an opportunity to see something we'd never seen before in the solar system. We saw 3 red spots on Jupiter. Now, we've seen the Great Red Spot continuously since about 1820. Actually, we might have even seen it as early as 1670, but we're not quite sure. Early in the 2000s, we saw the formation of Red Spot Junior, and this was the first time we'd ever seen a red spot form on the planet. And in May of 2008, we saw the formation of what we call the baby red spot. So, first time in history, we saw 3 red spots on the surface of Jupiter. Unfortunately, this didn't happen. This didn't last for very long, because over the course of 2008, we followed it, and you can see that baby red spot is on the same latitude as the great red spot, and over the course of that summer interacted with it and eventually broke up and no longer was a red spot at the end. So Hubble was able to follow the formation and ultimately the destruction of the baby red spot on Jupiter. Well, in 2009, Servicing Mission 4 finally happened. This was something that was scheduled for several years earlier, but due to this accident of the Space Shuttle Columbia, was delayed for several years. But in May 2009, we have this image of astronaut Drew Feustel working on his very first spacewalk, and during Servicing Mission 4, we installed 2 brand new instruments, Wide Field Camera 3 and the Cosmic Origin Spectrograph, to add to Hubble's capabilities. The early release observations were absolutely spectacular. This was one of the first early release observations, a planetary nebula called the Bug Nebula, although in our press release we referred to it as the Butterfly Nebula, and that name seems to have stuck. It really does fit, because it does look like a butterfly. These are actually hourglass-shaped lobes of material streaming away from the dying star at its center. Absolutely gorgeous, shows that Hubble is back in business. But this image, also from the early release observations of the central regions of Omega Centauri, shows off the new capabilities. This is a combined infrared and ultraviolet image. There's actually no visible light in this image. The red stars are the stars that shine bright in infrared, and the blue stars are the stars that shine bright in the ultraviolet, and we can pick out sort of the extremes of temperatures within Omega Cen with our new capabilities of Wide Field Camera 3. So, that is 19 years of Hubble imagery, and for the 20th anniversary, we had to come up with something spectacular. We had to say, all right, how are we really going to celebrate this? But we've got so much gorgeous imagery, could we really come up with something really spectacular? I happen to think that yes, we did. This is our 20th anniversary image, a pillar in the Carinae Nebula. Now, this is like the pillar in the Eagle Nebula in that the pillars are being carved out by those high-energy radiation and winds from bright stars, but it's absolutely a gorgeous, gorgeous view of a pillar in Carinae. And it includes, at the top of this pillar and the top of this pillar, jets from newborn stars. When stars first turn on, they send out these oppositely directed jets that spew out and announce their birth, where you can see them, a star that has just formed at the top of this pillar and one that has formed at the top of this pillar. This is an incredible image, and having learned what we did in creating the IMAX film Hubble 3D, we were able to put this one into 3D motion. In this animation, what we've done is we've taken the pillars in the Carinae Nebula, we've separated out layers of stars, we've separated out layers of the pillar, and we have pulled them into a 3D program and allowed us to fly through it in 3D to give you a sort of 3D feel. Now, this is not scientifically accurate, but it gives you a 3D feel for the structure of the nebula. So, that's it. That's 20 images for 20 years of Hubble. Now, 20 images is relatively small because Hubble has actually released over 1,000 public release images. It's taken nearly 1 million observations. We have released over 1,000 public release images, and here is a almost mind-boggling montage of Hubble images. So if I didn't cover your favorite one, perhaps you can see it in this montage. I'd like to finish with one last image. This is a sort of poetic image of Hubble hanging over the limb of Earth. But this image has even a little bit more meaning to us because this is the last image from Servicing Mission 4. And Servicing Mission 4 is the last shuttle mission to Hubble simply because the shuttle program is ending. So this is sort of the last view that humans had of the Hubble Space Telescope. Now you can see that Hubble is really just above Earth's atmosphere. And as an astronomer early on, I thought that putting Hubble in low Earth orbit was a problem because you've got the Earth there, you've got the Van Allen belt's radiation around it, you're going from day to night every 90 minutes. It really causes a lot of problems for astronomical observations. However, having Hubble in low Earth orbit and being able to send shuttle missions up to repair it has enabled Hubble to stay current. We are able to take out the old instruments and put in new technology which keeps Hubble current. You've seen the changes in this episode of the Hubble observations, but it also provides changes in what Hubble can study. Hubble has made significant contributions to the study of dark energy when we had no idea that that scientific problem was even going to be around when Hubble was on the drawing board. Changing out the instruments has enabled Hubble to not only increase its vision of the universe, but also to increase the number of scientific questions that Hubble can answer. And that is one of its legacies, that an orbiting observatory can change and adapt and address brand new problems over its 20 years. And of course, Hubble's not finished yet. After Servicing Mission 4, it is in wonderful condition. We expect it to last for another 10 years. Who knows, maybe more. And Hubble will be able to deliver a lot more beautiful images and a lot more cutting-edge science for years to come. Thank you for joining us. We'll see you next time on Hubble's Universe Unfiltered.